In this chapter, we're going to look at a number of applications of double integrals. I'm going to take these in a different order than the book. In the previous section, we worked on setting up double integrals over general regions by thinking about covering those regions with either vertical or horizontal rectangles. It turns out that we can take those ideas and use them to calculate the area of those regions. The key idea we want to work with is the same integration concept we've been using throughout the chapter. To calculate the total area, we want to cut it up into a bunch of little pieces and then add them all up. Here's the notation that should feel familiar. The dA term is sometimes referred to as the area element. And while this is formally a double integral, we should really think of it as an instruction that says cut up your region into a bunch of small pieces and add up their areas. The area element has multiple forms depending on the specific problem and application. Its value will depend on the shapes of the pieces you create when you cut up the region. So far, we've been working with rectangular regions based on how we set up the double Riemann sums a couple sections ago. We've been using dx times dy and dy times dx as the area element because that's from the formula for the area of a rectangle. This also means that when we're thinking about our regions, we've been cutting them up into little rectangular pieces. As the rectangles get smaller and smaller, we get better and better approximations. And as long as everything is mathematically nice, the limit converges to the correct value. It's worth noting that there are other ways to cut up a region, and if we use a different shape for the area element, then we end up with a different formula. In some cases, those alternative area elements are a better match for the region of integration, and this can lead to some computational simplifications. We will talk about this in more detail in a later section. You may remember that in single variable calculus, we were not only able to find the area below a curve, but we were also able to find the area between two curves. We want to elaborate on the connection between that formula and iterated integrals. For single variable calculus, we were calculating the area of a bunch of rectangles and summing the results. The difference term in the integrand is measuring the height of the rectangles, and the dx term corresponds to the width. When we were setting up the limits of integration for iterated integrals, we were looking at the exact same picture. Tracing out that vertical strip corresponded to the dy integration. In fact, we can rederive the formula by just working out the first step of the dy dx integral for the area. It's important to make these connections because this is what forms the foundation of other applications of integration. We're now going to switch gears and look at a particular application of double integrals. A lamina is a fancy term for a flat, thin object. It should remind you of the word laminate, as in putting a thin sheet of plastic over a sheet of paper. You can think of a thin disk of plastic as an example of a lamina. Our goal is to calculate the mass of a lamina, but we are going to consider cases where the lamina may not have a constant density. And so we have to figure out how to put mathematical language to this situation. Density is a ratio of mass to some unit physical dimension. In our case, we're going to be looking at mass per unit area because we're working with a flat, two-dimensional object. But this could just as well be a linear density or a volumetric density. Let's take a small piece of lamina at the point xy and calculate both the area and the mass of that piece. We can take that information to get the density of the lamina at that point. And if we do that for the entire lamina, we would get a function that tells us the density of the lamina at every point. We can also clear the fraction to get this useful relationship. The mass of a small piece of lamina is equal to the density multiplied by the area. This formula holds for any type of density if you replace the area element with the appropriate measurement for the given situation. Now that we've worked with the concept of density, let's try to get the total mass of the lamina. The total mass m is the sum of all those small masses dm. Each small mass can be calculated as the density multiplied by the area, which we will write as dA. So this is the formula for the total mass. From here, it's just setting up the integral as before. In many problems, the density formula will simply be given to you, and you'll need to make a substitution and do the calculation. But in some problems, you will need to come up with the formula yourself. Most of those problems will give you the density using phrases such as proportional to or inversely proportional to. As a quick reminder, if A is proportional to B, then we have A is equal to KB for some constant K. And if A is inversely proportional to B, then A equals K over B for some constant K. These two basic relationships can be extended to more complex situations. It's just a framework for how we express relationships between quantities. If the density is proportional to the distance from the origin, then we would have that delta of xy equals k times the square root of x squared plus y squared. If you pay attention to the language, you should be able to make the connection between the words and the equations. In the next couple sections, we're going to look at the concept of the center of mass of a lamina and take a look at some probability theory.